Starship V3 is about to change everything we know about reusable rockets. SpaceX is rolling out Raptor 3 engines with 280 tons of thrust, a redesigned hot staging system that stays attached through the entire flight, and thermal protection built for rapid turnaround. The booster will generate over 9,000 tons of thrust, nearly triple the Saturn V. So which of these 7 major upgrades will push us closer to Mars? Welcome to Space Update 24 Hours. Let's dive right in. Starship has always been massive, but SpaceX isn't satisfied with massive. The V3 booster will stretch from 71 meters to 72.3 meters in height, while the ship maintains its 52.1 meter frame from V2. Stack them together and you're looking at 124.4 meters of pure engineering ambition, taller than a 40-story building standing on the launch pad. But here's what most people miss. This isn't just about bragging rights. What does an extra meter of height actually unlock for deep space missions? The added length comes primarily from the upgraded hot staging system, which requires more vertical space to function properly. SpaceX is also expanding the fuel tank sections to feed those hungry Raptor 3 engines we'll discuss in a moment. When observers watched the first V3 booster, B-18, being stacked, they spotted something new, a redesigned fuel transfer tube snaking through the structure. Every centimeter of added height translates to more propellant capacity, more payload capability, and longer mission duration. And V3 is just the beginning, because SpaceX is already sketching plans for V4 that will push these dimensions even further. Which brings us to the engine that's rewriting the rulebook entirely. Raptor 3 isn't an incremental upgrade. It's a complete reinvention of what a rocket engine can be. Each Raptor 3 generates 280 tons of thrust at sea level and 306 tons in vacuum, making it the most powerful methane-oxygen engine ever built. That surpasses Blue Origin's BE-4 by a significant margin. But raw power is only half the story, because the real breakthrough lies in how SpaceX achieved it. The answer is radical simplicity. Raptor 1 and 2 were engineering marvels filled with delicate components, narrow channels, and tiny parts that could fail under extreme conditions. Raptor 3 strips all that away, eliminating hundreds of small components and merging them into larger, integrated assemblies. The result is an engine that's more compact, more unified in structure, and dramatically more reliable. Think about what happens during a launch. 33 of these engines fire simultaneously, generating over 9,000 tons of thrust. That's nearly 3 times the thrust of the Saturn V that took humans to the moon. If even one engine has a vulnerability, it becomes a point of failure for the entire system. So how does simplification prevent catastrophic failures? Fewer parts mean fewer things that can go wrong during the most violent moments of flight. No more tiny heat traps, potential leak points, or bolts that could vibrate loose. But the benefits extend far beyond launch day. Manufacturing becomes faster because there are fewer intricate production steps to complete. Raptor 2 already achieved a production rate of 1 engine per day, which seemed impossible just a few years ago. Raptor 3 could hit several engines per day, enabling SpaceX to build new boosters and ships at unprecedented speed. The simplicity also transforms maintenance and reuse. After a booster lands, teams need to inspect every engine for damage and wear. A complex engine with thousands of small parts requires extensive disassembly and testing. A simple engine can be inspected visually, tested quickly, and cleared for the next flight in a fraction of the time. This is how SpaceX plans to achieve airline-like operations, not by making inspection easier, but by making engines that need less inspection in the first place. And there's one more advantage. By eliminating unnecessary mass like heat shields and redundant components that earlier Raptors required, every kilogram saved gets reallocated to payload capacity. When you're talking about dozens of engines across 2 stages, those savings add up fast. This engine performance demanded a reimagined approach to stage separation. Earlier this year, Musk hinted at a major redesign for the hot staging system, and now we can see it taking shape on actual hardware. The new design takes inspiration from the Soviet N-1 rocket, which used a form of hot staging in the 1960s. But SpaceX has refined the concept with modern materials and manufacturing techniques. The biggest change is that the hot staging ring is no longer a separate component that detaches during flight. It's now built directly into the booster structure and stays there for the entire mission. This brings Starship one step closer to full reusability, eliminating the need to throw away expensive hardware with every launch. The connecting structures are less bulky than the V2 system, reducing overall mass and simplifying production. At the same time, the new setup improves heat dissipation during the critical moment when the upper stage ignites while still attached to the booster. The flames and pressure from 6 Raptor engines firing at full thrust create an environment that would destroy most structures in seconds. Can any material really withstand that kind of punishment repeatedly across dozens of flights? SpaceX's engineers clearly believe so, and they've integrated another critical upgrade just below the hot staging section. The grid fins and catching points have been completely redesigned and merged into a single unified system. Previously, these were separate mechanisms serving different functions. Now they work together as one cohesive unit. This consolidation reduces the number of moving parts and structural connections the booster must carry, cutting mass and simplifying assembly. The grid fins have also been repositioned slightly lower, now reaching the top of the fuel tank dome. This placement shields them from the direct blast of the upper stage engines during hot staging separation, reducing thermal stress and potential damage. Here's the surprising part. SpaceX reduced the count from 4 to 3 fins, arranged evenly around the booster. 3 fins provide the same steering and braking performance during descent while cutting manufacturing complexity and installation time. When you're planning to build hundreds of these boosters, every hour saved in production matters. While the booster receives these structural upgrades, the ship stage is evolving toward a capability that changes everything. When Ship 39 rolled out for stacking, observers noticed something new beneath the payload door, a structural cutout with no internal hardware installed yet. This is the refueling port, and while it looks incomplete, its presence signals something crucial. SpaceX is targeting in-orbit refueling demonstrations as early as June next year. Right now, Ship 39 serves as a test article to expose the interface to the thermal and mechanical stresses of launch and re-entry. The data from those flights will inform the final design before full integration begins. This might seem like a minor addition compared to the engine upgrades or structural changes, but it's arguably the most important upgrade on this entire list. Without orbital refueling, Starship's range is limited to low Earth orbit and brief excursions beyond. With it, missions to the Moon, Mars, and beyond become possible. Heavy payloads can reach distant orbits, and crew journeys extending far beyond Earth orbit shift from theoretical to practical. The refueling port isn't just a hardware upgrade, it's the gateway to deep space. But there's one system that must work flawlessly for any of these missions to succeed. The heat shield has always been one of Starship's most challenging systems. Re-entry generates temperatures exceeding 1,400 degrees Celsius, hot enough to melt steel. The thermal protection tiles must absorb and dissipate that heat while remaining intact for the next flight. Early versions struggled with cracking, chipping, and gaps that allowed dangerous heat intrusion. Ship 39 shows clear improvements with tiles installed with greater precision, tighter spacing, and more consistent structural layout. SpaceX is no longer planning to remove large tile sections between flights, a sign that V3 is transitioning from experimental testing to operational readiness. The materials and ratios appear to have been updated to reduce cracking, and the crunch wrap technique first introduced during Flight 11 has been further optimized to fill gaps between tiles and the underlying structure. Another change eliminates metallic tiles after testing revealed oxidation risks if cooling fluids leaked. These adjustments point toward a thermal protection system designed for repeated missions and rapid turnaround. Because as Starship takes on more demanding flight profiles, the heat shield must withstand higher stress while supporting fast reuse cycles. All of these vehicle upgrades would be impossible without matching improvements on the ground. Production capacity is expanding dramatically with the rise of the Gigabay, a manufacturing facility larger than anything SpaceX currently operates. It will introduce new assembly technologies and accelerate stacking operations. Combined with the 2 existing megabays in the Star Factory, SpaceX is positioning itself to build Starships at a pace matching next year's projected launch demand. Florida is preparing its own Gigabay as launch operations ramp up on the East Coast. Testing infrastructure is being reinforced following the Ship 36 incident, with new V3 support hardware being installed. Launch infrastructure is evolving just as rapidly. Pad 2 has been under construction for a year, receiving upgraded chopsticks, a new orbital launch mount, and a full-flame trench replacing the earlier steel plate design. Construction is essentially complete, and Pad 2 is expected to debut next month. Pad 1 is also being upgraded after completing its final launch under the old configuration, with similar changes underway in Florida. These 7 upgrades represent the most comprehensive evolution Starship has ever undergone, touching every system from engines to infrastructure. So which of these 7 upgrades excites you the most? Is it the Raptor 3 engines that could push thrust beyond 10,000 tons? The integrated hot staging system that finally achieves full reusability? Or maybe it's that refueling port, the small component that unlocks the entire solar system? Drop your ranking in the comments below, because I want to know what you think will have the biggest impact on spaceflight. Here's what we're witnessing. A year ago, the shift from V1 to V2 felt massive, but this transition to V3 is on a completely different scale. Every layer of the vehicle has been reimagined. Every system supporting it has been upgraded. SpaceX isn't just building better rockets. They're constructing the infrastructure to build them faster than anyone thought possible. The Gigabay will change production timelines. Pad 2 will double launch capacity, and those Raptor 3 engines will turn Starship from an experimental prototype into an operational spacecraft. The momentum is building, and we're not just observers anymore. We're watching history accelerate. V3 hardware is rolling out right now. Testing begins soon, and within months, we'll see whether these upgrades deliver on their extraordinary promise. If this breakdown gave you a deeper understanding of what's coming, hit that like button and share this video with anyone who needs to know about Starship's evolution. Subscribe to Space Update 24 hours so you don't miss what happens when V3 takes flight. The future of spaceflight is being built in real time, and we're covering every development as it unfolds. Thanks for watching, and I'll see you in the next one.